Okay, we're going to continue on here. Chapter 15, I think. Yes. Why not? Seems like a good chapter. All right. So, chapter 15 was about solutions. And as we talked about, there's really two parts to a solution. There's the solute, which is the smaller part of a solution. And there's the solvent, which is the larger part of the solution. Again, typically our solute gets dissolved in our solvent. For example, if it's a solid, so something that is ionic, like sodium chloride would be dissolved in water, which is polar. Now, we talked about sort of different types of solutions and the idea really of like dissolves like. And remember, the idea here is in terms of sort of solubility, things will be soluble. Thank you. Things will be soluble in things that really sort of behave the same way that they behave with themselves. In essence, they use sort of the same intermolecular forces as they do with themselves. So those things like we talked about in the last chapter as well, which is like our dipole-dipole, hydrogen bonding, dispersion forces. So things that are ionic and polar are going to be soluble in each other. Again, they're going to basically use sort of that ion dipole interaction. And that's essentially, as we talked about, sort of what happens when we dissolve something, say like sodium chloride in water. The ions get surrounded by the different sides of water. Positive surrounds the negative ion, and the negative side of water surrounds the positive ion. Things that are polar and polar are typically soluble in each other. They would either use like a hydrogen bonding situation or like a dipole-dipole situation, and again, makes them very, very soluble in each other. One of the sort of interactions sometimes people overlook is this one. If you have something that is nonpolar and nonpolar, they also are going to be soluble in each other. And that is because they will both be using dispersion forces. So, although that dispersion forces are a relatively weak intermolecular force, when you have two nonpolar molecules coming together, they're both using the same type of force. So they're able to interact really well with each other. Now, when we sort of have all these guys, usually they are soluble. When we have the crossover, sort of a polar guy with a non-polar guy, that's really where we sort of run into trouble. And usually those guys are going to be insoluble in each other. And it's really because, as we talked about, they're using very, very different and try to use dispersion forces. So over a long period of time, they really have no way to keep that interaction going. And they typically are going to be insoluble in one another. Also, as we also talked about, these sort of intermolecular forces affect things, obviously, like solubility, like we're talking about here. They also affect things like melting points and boiling points. So if you have a relatively strong intermolecular force, which out of the three, hydrogen bonding is the strongest, it should have a higher boiling point, melting point than something that's using dispersion forces, which should have a much lower melting point, boiling point, because it's a weaker type of intermolecular force. We talked about unsaturated solutions. In an unsaturated solution, you basically can still dissolve more solute in it. So it has not hit that point where if you try to dissolve something in the solvent, it will stop. It will continue to dissolve, and it will continue to be able to dissolve until you hit, as we talked about, a saturated solution. And that saturated solution is really the point where you pretty much have hit the maximum amount of solute that will dissolve. And it is based on temperature, as we talked about, at a given temperature. And really, if you're at a saturated solution, you've hit that maximum. And if you try to dissolve any more solid in there, you're not going to be very successful. It's not going to really dissolve. It's just going to sort of pile up. We also talked about our super saturated solution. And our super saturated solution is one, as we talked about, as we saw in person and on that little animation video as well. It's a solution that really has way too much solute dissolved in a solvent at a given temperature. It is, as we talked about, the way you make it. You will end up with a solution at the end, but it's a very unstable solution because the process of typically making a supersaturated solution is you heat it up, which increases the solubility. But then you let it cool back down and that decreases the solubility, but you're already in the solution sort of state, if you will. And at that point, if you just add one little crystal or kind of bang it too hard, all that solid will come out of solution because, again, it's too much at that cooler temperature to be dissolved in there. I think we finished up also talking about concentrated solutions versus dilute solutions. And a dilute solution versus a concentrated solution. A concentrated solution, again, is one that has a lot of solute dissolved in it. It's a pretty strong solution. A lot of times we use more dilute solutions, say in the laboratory, and that's, as we will talk about, basically take a concentrated solution and you dilute it down by adding more solvent in that particular case. Any questions on any of that stuff there we talked about last time? Yeah. Then we are off to some calculations. So we're going to talk about some important types of concentration units. We're going to start out with some percent concentration units. This is mass percent, or sometimes abbreviated percent M/M, which means mass to mass. It is basically the mass of the solute over the mass of the solution times 100%. It's essentially kind of usually grams over grams in terms of the units. They do cancel out at the end and become just a percentage. It's really important in this particular one that you look at the mass of the solution. The mass of the solution part is both parts of a solution, which is you want to make sure that you get both the solute and the solvent together. And that's really important when you're doing this calculation. And I would say it's important because probably in these type of problems, they very often will give you the mass of the solute and the mass of the solvent separate from each other in the problem. So it's a very common mistake that people make is they just kind of grab the larger number, which is the solvent, and just divide by the solvent and not really the solution. So very commonly given to you separate numbers. You have to usually add them together to make sure that you get the mass of the entire solution there on the bottom, and you can times it by 100. Now, if you had a, say, 4.5% by mass sodium chloride solution, a lot of times we may want to do some calculations with this, and we're given the mass percent. Like any other percentage, probably the easiest way to turn it into sort of a usable type number is to assume that you have 100 of it. So what that would mean if we wanted to like turn this into, say, a conversion factor to use in a more dimensional analysis type of a calculation, that would mean that you would have 4.50 grams of sodium chloride in 100 grams of solution. And like any other conversion factor, if you needed to, you could flip it around and go in 100 grams of solution. You would have 4.5 grams of sodium chloride. So very commonly, you will be given perhaps the percent by mass or percent mass to mass. And if you just kind of turn it into those kind of conversion factors, number stays the same. It's always out of 100 grams. Sometimes it's easier to sort of do the calculation rather than just plug it into the formula here. Which you could still obviously just plug it into the formula and solve for what's missing, but you can set it up more so you can see the units using that. Any questions on that there? A couple of other sort of percent concentrations that we come across is percent volume to volume, which is the top one here. So this is basically percent volume to volume. like an alcohol, percent by volume alcohol. Percent volume to volume is the volume of solute divided by the volume of solution times 100%. And percent mass to volume here. So this is percent mass to volume. And it is basically here the mass of the solute over the volume of solution times 100%. Top one is typically, in a lot of cases, not always, but milliliters over milliliters, basically. Bottom guy is basically grams over milliliters in most cases, kind of like density, pretty much is what you got there. Again, they both become percentages when it's all said and done. Unlike the previous one, which is mass percent, with these, in most cases, you don't have to worry too much about the bottom. Usually it's given to you as just the volume of the solution, or you're able to actually get the volume of the solution. So it's really just the first one you usually have to kind of worry about in terms of that bottom part of it. Just like the other one, if I had the 4.5% by volume sodium chloride solution, it would mean I have 4.5 milliliters of sodium chloride in 100 milliliters of solution. And once again, you could flip it around, 100 milliliters of solution divided by 4.5 milliliters of sodium chloride. Same thing down here. If we had a 4.5% mass to volume sodium chloride solution, that would mean you had 4.5 grams of sodium chloride in 100 milliliters of solution. And again, you could flip it back around, 100 milliliters of solution over 4.5 grams of sodium chloride. So again, just like the other ones, sometimes it's easier to kind of turn them into a conversion factor and do the calculation more of a dimensional analysis approach. But just like the other one, you could also just kind of plug and chug into the formulas as well and solve for what you need. Any questions on any of those there? All right, let's try one here, perhaps. A solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams of water. What is the mass percent of the solution? So we're looking for the percent mass to mass here of this guy. Take a few moments, see what you come up with. Okay, so let's take a look. We're looking for our percent mass to mass here, which should be our mass of our solute divided by the mass of the solution times 100%. In this case, our calcium chloride here would be our solute, as that is the smaller part here of our solution. The water here would be our solvent in this case, which is the larger part of the solution. So we have our mass of our solute, 2.5 grams, our mass of our solvent, 50 grams. Remember that we do need to add them together here to get the mass of the solution, which is 52.5 grams in this case. Now we have correctly the things that we need. Again, we do not want to divide by just the solvent in this case. So 2.5 grams divided by 52.5 grams times 100%. And that will get us here 4.76% mass to mass. You could call it calcium chloride in this case. Any questions on that calculation? So again, very common mistake, just divided by the solvent, and they're usually separated in these type of questions. Any questions on that one? Let's take a look at another one here. Concentrated hydrochloric acid contains 37.2% by mass hydrochloric acid. what is the mass of hydrochloric acid that's contained in 35.5 grams of this concentrated hydrochloric acid? In this case, we are given the percent mass to mass, which is 37.2%. We do have the mass of the solution given to us, which is our 35.5 grams. We are looking for the mass of the solute. So how do I know I'm looking for the solute and that this guy was my solution? A reminder that the name of the solution is the solute. So when you're asked for how many grams of HCl in an HCl solution, then you're definitely looking for the mass of the solute. And that would mean by default, the other number that they gave you was the solution. So that's how we sort of know it. One way you could do this is you could just plug and chug into there. You could also, again, take a more dimensional analysis approach, which is how I'm going to solve it, I think. So again, this 37.2% means that I have, in this case, 37.2 grams of HCl and 100 grams of solution. And again, we could use it in the opposite way. 100 grams of solution is 37.2 grams of HCl. By doing it this way, we could just take our 35.5 grams of solution and just do a dimensional analysis where we go opposites cancel. So we'll use our conversion factor there on the left. Then we don't have to worry about remembering perhaps the equation too much here or rearranging it incorrectly. We could just do it like that. And we will end up with 35.5 times 37.2 divided by 100 gives us that there are 13.2 grams of HCl in this case. Obviously, as well, you could plug and chug into the formula, which would be 37.2% equals the mass of our solute divided by our 35.5 grams times 100%. And you would essentially be doing the same math, right? So basically the same. So whichever way you want to do it, you would multiply the 35.5 to the other side and divide by 100, which is, again, basically how we did it with our dimensional analysis. So if you do it that way, dimensional analysis way, you could just kind of do a get rid of the units you don't want, keep the units you do want, and maybe don't have to remember too much of the formula. Any questions on that there? So these are a couple of concentration type units, which are used occasionally. But let's talk about really the main type of concentration unit that we use the most, or that we do see the most. And this is molarity. And molarity is abbreviated with a big M because a smaller m means something else. So molarity here is actually moles of solute over liters of solution, or moles per liter. You should look at molarity really like a formula. So molarity is moles per liter. That means if we want to solve for liters, which is a very common calculation, it is moles divided by molarity. If we want moles, which is also a really common calculation, we take liters times molarity. These are three ways, obviously, to rearrange this equation or use this equation. And I will say in probably a lot of problems, we use all three versions here. Sometimes we want to calculate the molarity. A lot of times we want just the volume. And a lot of times we need the moles. So very, very common to sort of use this. Again, you can kind of think of it almost like the density equation, where you really, in a lot of cases, will solve for all three of these things or use all three of these things along the way. Now, when we have molarity, or somebody tells you it is a 4.5 molar solution of sodium chloride, like they say 4.5 big M sodium chloride, and that's how you would say it, 4.5 molar sodium chloride. It is really important, I think, when you do calculations, and I highly, highly, one more time, highly recommend that when you do the calculations, you actually get rid of the big M. And the reason for that is, I'll tell you in a second, but really the way she uses is more like a conversion factor of 4.5 moles per liter. And the number always stays with the moles, and it's always 1 liter, basically. You could use that like a conversion factor, which means you could flip it around and use liters on top, 4.5 moles on the bottom. I would highly recommend that you kind of use it like a conversion factor, especially if you're given the molarity. You get rid of the big M and show both units. The reason why you want to really do that is I can't tell you how many papers I have seen over the years where people leave the big M and all they think about is moles. And they have no idea about the volume part of it, the liters, where the liters are. There are liters involved. They just sort of forget about the volume part of it. So it's really important to kind of get rid of that big M and just convert it into moles per liter. That way you can visually see when you're doing your calculations, both units, and hopefully you won't forget about the liters part of it. And once again, number always with the moles, always 1 liter when you do that. Any questions on that? That's also really important because when you do this calculation here to figure out the moles, the volume should always be in liters. Yeah. Otherwise, you may leave it in milliliters, which is a very common thing that people do. Not that it will not work right for you, but it probably won't, because you can multiply molarity times milliliters. So if you took milliliters, for example, and you times it by molarity, you actually don't get moles, which is probably what you're looking for. You get what are known as millimoles, which means you're about 1,000 factor off of what you're probably looking for. And you don't want to do that. So if you're ever using molarity by itself, you're using volume by itself, always make sure it's in liters. That will give you moles, which is probably 99.9 of the times the unit that you're looking for. So you'll have the right unit when you do that. That's why sometimes you will see that molarity is also millimoles over milliliters. And that is because the milli on top and the milli on the bottom cancel. And now you have moles per liter, which is molarity. So if you take millimoles and divide it by milliliters, it all works out okay. But in a lot of cases, you're looking for moles. So always make sure, I would say, molarity by itself in a concentration problem, the volume should be definitely in liters. Any questions on that there? So as I mentioned before, if we have a 1 molar solution of something like sodium chloride, that does mean that we have 1 of sodium chloride in 1 liter of solution. And that also means in terms of ions. So how does sort of ions work? A lot of times we have ionic compounds like sodium chloride. And if we throw sodium chloride and dissolve it in a solution, really what we have floating around in there are ions, right? And that's really what's floating around in that solution. The sodium chloride is a strong electrolyte. It's not going to stay together, which means it's going to 100% break apart into those ions. So sometimes when you're dealing with concentration, especially concentration of ions, you sometimes are interested in maybe what the concentration of just the ion part of it is, not the whole thing. So for example, if I have something like sodium chloride and how sort of molarity works with, not M, but how it works with the ions here. Something like sodium ion and chloride ion here. If this guy was 1 molar, you could look at it and sort of do it like stoichiometry by looking about sort of the coefficient. And for every one of these guys, right, I get 1 sodium ion. So if I was interested in the concentration of just the sodium ion that's floating around in that solution, you basically take 1 times 1 molar, which means the concentration of the sodium ion here would be also 1 molar floating around. If I look at the chloride, it is a 1-to-1 relationship between those two guys as well in terms of how it breaks apart. I would also take 1 times 1 molar. and that would give me 1 molar as the concentration of the chloride ions. Obviously, concentration is not additive because 1 to 1 is 2, not 1, but it's sort of the proportion of what you get when it floats around. Let's say I had, though, something like, let's say we had barium bromide here. We'll do that. So if I had something like barium bromide solution, when it breaks apart, we will get a barium ion and 2 bromide ions, right, when that thing goes for a swim. So unlike our kind of sodium chloride sample here, we took a little barium bromide and threw it in there, we would get a barium ion floating around and a couple of these guys sort of floating around as well. So when we look at the concentration of the whole thing to just the barium, and this guy was 1 molar as well, it would be 1 times our 1 molar, which means it would be 1 molar of barium ions floating around. But when we look at our bromide, it's a 1 to 2 relationship here, which means we could take 2 times our 1 molar, which means we have 2 molar in terms of the bromide. What that basically means is twice as concentrated, right? Bromide ions versus barium ions, right? It's like 2 for 1 type deal. So we got twice as much of that barium bromide as we do barium, which is why the concentration is twice as much in this case. Any questions on that? That is really the sort of fast way to do that calculation to figure out, what is the concentration of an ion. Let me show you really the long calculation of it and sort of why we multiply by 1 or multiply by 2. For example, we just looked at the barium bromide. We could start with our 1 molar barium bromide, moles per liter of barium bromide. We could then do our mole to mole relationship, which is a 1 mole to 1 mole relationship. So for every 1 mole of the whole thing, I feel like I'm putting the R in the wrong spot. There we go. We get 1 mole of barium here, ions, which gives us 1 mole of barium ions per liter solution, which is basically our 1 molar barium. When we do the same thing, starting with our whole thing here of barium bromide, it is a mole to mole relationship like stoichiometry, a 1 to 2 relationship here. So for every 1 mole of barium bromide, we get 2 moles of Br minus. Moles of those guys cancel, gives us 2 moles of Br minus per liter, our 2 molar Br minus. So times it by 2, times it by 1 basically is the shortcut down here. So you can do the long version of that calculation, or basically whatever it breaks apart into. If you want the molarity of just the ion by itself, efficient. So if it broke apart into a 1 to 3 relationship, you would multiply the molarity by 3 and so forth. Any questions on that there? So again, sometimes we may not be interested in everything. Yeah, you can leave it as moles per liter. Or in place, you can at the end put the big M back in terms of the unit. Yeah. All right, so that's again something that we do come across where we're looking again at just sort of the ions versus the whole thing. If you're just looking at the whole thing and not the ions by itself, you obviously can just keep it together. You don't have to sort of figure out each of the ions concentrations. So let's take a look at one here. Calculate the molarity of a solution prepared by dissolving 15.6 grams of solid potassium bromide and enough water to make 1.25 liters. Potassium is 3910 and Br is 7990. All right, so take a few minutes. We're looking for the molarity of this solution here of the Kb molarity, which is our big M. Again, that is moles per liter. We can see already off the bat here, we kind of have the liters part, so we don't have to do anything to it. I would say as well, a very common sort of conversion that you sometimes have to do in molarity is milliliters to liters. So a reminder that there are 1,000 milliliters, right, in 1 liter. That's a very common sort of conversion in terms of the volume part of it that you have to use a lot. In this case, we don't because we do have it in liters. We do need moles, and that is our solute here, and it is not in moles. So we do need to take our 15.6 grams of KBr and convert it to moles. This is also a very common conversion that you need to do. And as we've done many times, hopefully up to this point, that is the molar mass from the periodic table that we need. So we're just going to add these guys together actually. And that's going to give us 119 grams per mole. We will use as a conversion factor here to get rid of grams. So the grams will go on the bottom. The moles will go up on top. Grams will cancel. That's going to give us 15.6 divided by 119. We'll go with 0.131. And that is the top part there that we need to calculate the molarity. So all that's left to do is actually plug those guys in, 0.131 moles per 1.25 liters, going to get us here like 0.105. Now, in terms of the units, you can leave it one of two ways. You can leave both units because they really don't cancel out. And again, the number would stay with the moles part. It would be 1 liter. And you can throw the KBr in there as well. Or if you wanted to, at this point, once the calculation is done, you can pop it back in as just a capital M and do KBr. So those, again, are kind of two ways that you can leave the answer. Each way is okay. Any questions on that calculation? So again, very common grams to moles using the molar mass, and also, like I said, milliliters to liters using that 1,000 to 1 conversion. Let's take a look at another one here. What is the mass in grams of sodium nitrate that's required to make 2.5 liters of a 0.15 molar sodium nitrate solution? Sodium is 2299, nitrogen 1401, and oxygen 16. Okay, so let's take a look. Obviously, we're dealing with molarity here, which is our moles per liter. We are given the molarity, so we have that. We are also given the volume. So if you weren't sure where to go, moles is really the only thing we are not given, which does make sense as we're looking for grams, because once we get the moles, we could then go to grams using the molar mass from the periodic table. So we're going to rearrange this really and solve for moles. Moles here will be liters times molarity, which is a very common sort of calculation we do a lot in chemistry. We obviously have the volume here of 2.5 liters. Now, remember that the molarity, as I mentioned before, really a good idea to get rid of the big M and show both units. And this would be our sodium nitrate. And you could use it, like I said, as a conversion factor. And that means if you needed to, you could also flip it around and sort of do the same thing. And that's the way I'm going to approach it. It's just more of a dimensional analysis question. And we're going to start with our volume here. And we want to get rid of it. So opposite means we're going to use it just like that. And that's going to give us 0.15 moles of sodium nitrate per liter of solution. The liters will cancel in this case, and that will give us 2.5 times 0.15, 0.375 moles of sodium nitrate. We once again now just need the molar mass from the periodic table to get to how many grams. So there's 1 sodium at 2299. There's a nitrogen at 1401. And there are 3 oxygens at 16. And that's going to get us here Looks like 85 on the nose there. Remember, we're going to use this as a conversion factor. So once again, we do want moles to cancel. So the grams are going to go up on top. Moles will cancel. And that will give us here about 31.9 grams of sodium nitrate in this particular case. Any question on that calculation? So again, in this case, I would definitely probably take more of a dimensional analysis approach so you can kind of see the units, get rid of that big M, so you know where the liters are. And by the way, like we might have talked about before, by doing it more of this dimensional analysis way, I don't really even have to sort of worry about rearranging this equation. I just need to go opposites to cancel. And I know, again, top multiply, bottom divide, I'll just do the math correctly as well. So again, it just makes it a little bit easier and a little less, maybe room for error there. Any questions on that? By the way, that number means that if I wanted to make the solution, I would need to go grab my sodium nitrate. I would need to measure out 31.19 grams of it, put it in there, add enough water to get a total volume of 2.5 liters to dissolve it in, mix it really well. And if I do that, I then will have a solution that has a molarity of 0.15 molar, basically. So again, that's what that number basically represents. That's how you would go make this solution. Just dissolve that many grams of water. Make sure you hit exactly 2.5 liters, mix it up really good, and you'll have a solution that has that molarity. Any questions on that there? So why don't you try this? What is the concentration of each of the ions in these two separate solutions? So for the first one, 1.2 molar sodium sulfate. What is the sodium ion and sulfate ion concentrations? And for the other one, 0.75 molar K2CrO4. What is the concentration of K plus and the CrO4 2 minus in this case? All right, so let's take a look. So once again, really a good way to do this is just to figure out how it's going to break apart here, and then you could basically relate the concentration of the whole thing to each of the ions. In this case, we are going to get a couple of sodiums when this breaks apart, and we are going to get one sulfate. So again, in terms of the concentration, if the whole thing is 1.2 molar, it is a 1:2 relationship here, which means we do need to multiply that by 2, the coefficient. And that means that the concentration here would be 2.4 molar of the sodium ions floating around. When we look at the sulfate, it is a 1:1 relationship, which means we basically just going to multiply it by 1, or it will stay the same. And it would be 1.2 molar for our sulfate. And this is for our sodium there. Any questions on that one there? We'll do basically the same thing here for our second one. We'll figure out how it's going to break apart. It's going to break apart kind of similar here. So we got K2CrO4. Because this is a strong electrolyte, it will break apart into 2 K pluses and 1 chromate here. Again, just using really like our sort of stoichiometry sort of approach here. We're going to basically multiply the first guy by 2 because it's a 1:2 relationship here. So 2 times the concentration of the whole thing will get us 1.5 molar potassium ions in this case. And it is a 1:1 relationship between the second guy, which means we're just going to multiply it by 1 or really just keep it the same, which means 0.75 molar of our chromate. So again, this would be a question where maybe they're not interested in the whole sort of ionic compound together, but really want the concentration of just the ions that are floating around really in the solution. And again, more of a stoichiometry sort of relationship. Any questions on any of those there? All right, so let's try one like that ish here. How many moles of calcium and chloride ions are there in 42 milliliters of a? We could kind of approach it, but we're definitely dealing still with molarity, which is our moles per liter. We are given the molarity. We're not given the liters, but we are given the milliliters, which again means that we do want to solve for moles here. Moles would be our liters times molarity. So that obviously tells us we do need to convert that guy into liters to do this correctly. In this particular case, we're not really looking for the moles of the entire thing together. We're looking for the moles of each of the ions that are present. So one way you could do it is just get the concentration of each of the ions first and then do the calculations. Or you could do it with the whole thing and then do the calculation and convert it over. So for example, here we know that we have calcium chloride. When this breaks apart, we will get one calcium ion and two chloride ions in this case. And we could do the same thing we just did. That is 0.35 molar for the whole thing. It's a 1-to-1 relationship here, which means that this would also be 0.35 molar by basically just timesing it by 1 for our calcium ions. We could also do the same thing for the other guy. It's a 1-to-2 relationship, which means we'll take 2 times the 0.35 molar. And that's going to get us there 0.7, I believe. 0.7 molar of our chloride ions. So now that we have kind of the concentration of each of the ions separately, we can then go into our equation for each of them here. And if we wanted the moles of calcium, I'm going to take my milliliters, which I first need to convert. So 42 milliliters, 1,000 milliliters is a liter. That puts it in the correct units here, which is what we need. Again, always liters when you're using molarity by itself. I am again going to take this 0.3 big M of calcium and convert it into a conversion factor of 0.35 moles per liter of calcium once again, so I can see both of the units here. And that actually is the way that I need to use it. I could also have flipped it the other way if I needed to, but in this case, that happens to be the right way. The liters here will cancel, and that will get me 0.35 times 0.042, 0.0147 moles of calcium ions are basically floating around in there. Any question on that part of the calculation there? We'll do the same thing for our chloride. So our moles of Cl minus would be still the same volume, converted to liters. Just like the other one there, I'm going to turn my 0.77 big M into moles per liter of chloride. Again, showing both of the units there. And that also is the way that I need it. So that is the way I will use it here. 0.7 moles per liter of chloride. Liters will cancel. 0.042 times 0.7, 0.0294 moles of chloride in that case. Obviously, if I wanted grams of each of those, I could use the molar mass, right, of calcium and chloride and get the grams. Question on that. Now, the alternative approach that you could have done was this. You could have just did it like a sort of normal calculation, which means you could have took the volume converted to liters like we did. You could have used the molarity of the entire thing here. And again, you could have went 0.350 moles of calcium chloride per liter, and those guys would have canceled. And you would get 0.0420 times 0.35 gives you 0.0147 moles of calcium chloride. And then you could have just done like a stoichiometry mole to mole relationship, 1 to 1. 1 mole of the whole thing gives us 1 mole of calcium, gives us 0.0147 moles of calcium ions, which obviously is what we got here. And instead, you could also have done a up to this point and swapped it out for the other guy and did 2 moles of Cl minus 1 mole of the whole thing instead of what's there. And that would get you to that guy. So you could have done the whole thing and then just kind of did a mole to mole relationship. And really, that is what we were doing here, kind of that mole to mole relationship at the beginning instead of at the end. So you could have done it that way as well. Any questions on that? Questions on molarity. Obviously, you need to be able to calculate molarity, figure out volume, R moles, if you're given any of that information. All right, let's talk a little bit about dilution then. Good talk? No. So when we dilute something, as we talked about before, a lot of times solutions do come as more concentrated solutions, which means they contain a relatively large amount of solute in them. And a lot of times we basically do a dilution. And basically when you do a dilution, the only thing that you add is typically more solvent. And I will say a lot of times you're going to add more water. Remember, water is a solvent for a lot of things, but not everything. But so technically speaking, when you're doing a dilution, it is just adding more solvent. But 9 times out of 10, probably less by adding more in this case. So when we add more water, or we dilute it with adding more solvent, the molarity actually changes. And that's something to keep in mind as you go through your chemistry career. If you ever add more solution or solution to solution, the molarity actually changes. And the reason the molarity changes is if we look at what the definition of molarity is, it is moles of the solute divided by liters of the solution. And remember that the solution is both the solute plus the solvent. So when you do a dilution, you're actually adding more solvent in this case, which actually makes the bottom part here larger. And that means that the molarity typically will go down in this case because you're diluting it by adding more solvent in this case. That also means that every time you add more solvent, the molarity constantly changes because you're changing the bottom part of it. The one thing that doesn't change though, when you do a dilution is if you look at the molarity equation, it's the top part. We didn't do anything with the solute. So the solute doesn't change. So the moles of solute, whatever you got dissolved in that solution, in terms of the solute to begin with, you'll have the same number of moles after you do the dilution. So the moles of the solute before and after will be the same. By the way, when you have a solution, it is the solute that's actually doing any type of reaction or anything like that. That's actually what's available to do a reaction. It's like those sodium ions floating around, those chloride ions floating around, for example. Those are the guys actually doing the reaction. So when we do a dilution, and here's one way you could do it. You could take a little bit of water, a more concentrated green solution, and then you could top it off with some more water here. And that will give you a diluted solution. This is a volumetric flask that we talked about, I think, last week. Very expensive, typically has 1 line. And again, that line represents the volume that's in there. Typically speaking, that is 2 decimal places, by the way, when you use volumetric. So that'd be like 500 milliliters. You put it in there, you'll fill it to the top, put the cap on, mixy, mixy, shaky, shaky, right? And you'll have hopefully your solution that's what you're looking for. As we also talked about last time, if I actually went over the line here and ended up here, can I just pour out the extra? You cannot, right? Because some of your solute's in there, right? Either you dissolved it already or it's in the solution that you're diluting to begin with. And by the way, you could obviously dilute a solution by adding water to it. Also, take a solid, make a solution and dilute it as well. So you don't want to do that because again, you would not have the right molarity. So to calculate a dilution, I would say most people use this equation. I personally use it for every situation because molarity really is sort of the most common unit of concentration. You could use this one, which is M1V1 equals M2V2. This is sometimes referred to as the dilution equation. This is really before the dilution. These guys on the other side is usually after. It really doesn't matter as long as you keep the numbers that go together together. M is molarity, V is volume. M on the other side is the molarity after you do dilution, and V is your total volume of the solution that you made. Now, you can technically, and sometimes books will use this one nowadays, C1V1 equals C2V2. It's the same equation. C is just generic for concentration, which means technically speaking, you could use any type of unit of concentration, like we did percent mass, mass, percent volume, volume. You could throw those in there into this equation as well, and it will come out the same. Now, one thing that I will say, if you use this equation here, and this is the only situation that you probably should do this, which is if you want to leave the volume in milliliters using the dilution equation, it's all good. It will work out okay. So if you want to leave it in milliliters using this equation, 1V1 equals M2V2, everything will work out okay. For example, if I was solving for M2, it would be M1 V1 over V2. And if we just look at units, molarity, and I leave it in milliliters, divided by milliliters, they cancel, and you're still left with molarity at the end. So it will work out okay. If you want to convert it to liters, you could do that as well, as long as it's liters on both sides. You can do that. Obviously, if you have milliliters in terms of a volume and you're solving for a volume, your volume will be milliliters. If you have a volume that's in liters and you solve for volume, it'll be in liters as well. So this is the one place that it's okay to do that. If you are, again, not doing a dilution, but doing just molarity and volume, convert it to liters. So you'll be in the right units and you won't be on the wrong units. So let's take a look at one here. What volume of 19 molar sodium hydroxide is required to prepare 1 liter of 0.15 molar sodium hydroxide solution? So what we got going on is we have a bottle over here that is 19 molar sodium hydroxide. And we want to make a new sort of container that has a volume of 1 liter, or that's basically 1,000 milliliters, right? And a molarity that is 0.15 molar. So we could use our M1V1 equals M2V2 action. These guys are typically after dilution, so this would be like our M2V2. This would be our M1, which means we're looking for really V1 here. It's the only thing that we don't have. So V1 here would be M2V2 M1, dividing the M1 to the other side. Putting in our numbers, we will get 0.15 molar times 1 liter divided by 19 molar. Molarity will cancel. And in this case, what we will end up with here is 0.00789 liters, or approximately 7.89 milliliters of sodium hydroxide. So what that number means is if we want to make the solution, we would come in here and I'll just do it in milliliters, 7.89 milliliters, right, of our sodium hydroxide. The rest would be water in this case. Would I add 1,000 milliliters of water? I would not want to add 1,000 milliliters of water in this case because my total volume would now be like 1,008 milliliters-ish, right? Which is too much. So a very common dilution sort of question is like, how much water should you add? I know my final volume, right, is 1,000 milliliters or 1 liter. I know that I already put in there 7.89 milliliters of our more concentrated solution. So I take 1,000 minus 7.89. That means that I need to put in there 992.1 milliliters of water with it. So that's what I would do. Go in 992.1 milliliters of water. That will give me my total volume of 1,000 milliliters or 1 liter. I would mix it up really good at that point, and then I should have a solution that is a concentration of 0.15 molar. So a lot of times to find like the volume of water or the solvent, we oftentimes take V2 minus V1, and that is a very common dilution type question, which is like how you would make it, how much water you need to add, or something like that.